All right, so last class we were talking about different ways of expressing concentration. All right, and so we hopefully got to practice some of the homework problems where we were changing concentrations in terms of molarity, molality, mass percent, mole fraction. Okay, so if we're looking for an answer to this question here, which of the following corresponds to 3.5 molar solution with that density? Okay, we would need to identify this M here. What is that M there, Camille?
That
Molality,
molality.
very good. Sarah, what is this here? This X NaCl?
That is mole fraction.
Mole fraction, that's right. And then this percentage, Aisha? Mass percentage. Okay, very good. Now, we are going to break up into some what do you call them? Breakout rooms. We're going to get into some breakout rooms and try to solve this together with some neighbors. Okay, so let's see if we can do it. All right. Hopefully everybody's able to participate a little bit. Okay. See you in your rooms. Camille, are you available to answer some questions? Is your mic working?
Can you hear me?
Yeah, did you get to work in a group at all?
I couldn't figure out how to get back into my group because I had to leave.
Okay. Alyssa, did you get to work in a group at all?
No, I didn't.
Okay. Aisha, did you? Did you get to work in a group, Aisha? Landon?
No, Aisha's mic wasn't working.
All right. Well, Sarah and I had a great time. It was a great party. You guys should have been there. You really missed out. Landon, do you think you can give us some ideas how you would solve this problem, or did you get to solve it?
No, I
You didn't. Okay. Well, Sarah, I guess you're going to tell them how to do this problem.
Okay. So I started with the molar. They give you the molar concentration, which is we have 3.5 moles per 1 liter of solution. And so I just worked on finding the molality first, and molality is moles of solute per kilograms of solvent. And so for the molality, we already know that we have 3.5 moles of solute. And so to find the kilograms of solvent, we're given the density, which is 0.997 grams per milliliter, which you can also say is 997 grams per liter. And did I... Okay, so to find out how many grams of water we have, we need to figure out how many grams of NaCl we have. So we have 3.5 moles of NaCl, so you can just multiply that by its molar mass, which is 58.44. And that gives you 204.6, I believe.
Okay, 204.5.
Yeah.
Okay.
And then, so we have 997
Whoops, no.
yeah, that's our total.
This is grams of solution. Wait, oh, no, sorry. This is grams of solution per liter of solution. Sorry, that's the density right there. That's grams of solution per liter of solution. So yeah, 997 total grams of solution. Yeah.
Yep, so subtract 204.5 grams of NaCl from 997 total grams of solution.
So because the grams of solution is made up of grams of NaCl and grams of water, you're saying if I take the 204.5 grams of sodium chloride and remove it from the 997, then whatever is left over must be the grams of water, right?
Exactly what I'm saying.
204.5, and how much did you say you got? 792?
Yes.
Did I do that right? 792.5. All right, so what does that do for us?
So, for molality, we need the kilograms of solvent, and we have the grams of solvent, so we can just convert 792.5 to kilograms, which is 0.7925. And, yeah.
Okay, so then 3.5 divided by 0.7925 should be our molality. 4.4. Okay, so we got 4.4 for our molality. And then we also, the party didn't stop there. We went on and did the mole fraction. Now, mole fraction means moles of solute over moles total. And moles of solute was 3.5 moles of sodium chloride. Now, moles total has to be this 3.5 plus the moles of water. And then that ratio right there would be my mole fraction. So where do we get moles of water? Well, we just calculated that I had 997 grams of solvent. That's grams of water. So 997 grams of water. And if I want to get that in moles of water, then I can go 18 grams of water for every 1 mole of water. And
I have a question.
Yeah.
I thought we found that the grams of water was the 792.5.
Oh, yeah, that's right. 792.5. 792.5 was gram. 987 was grams of solution. So 792.5 divided by the 18 44.02. What is that telling me? That's my moles of water. So 44.03, 44.03 moles of water. I can add that to the moles of sodium chloride. And then I can take the moles of sodium chloride and divide it by the total there. So it should be a mole fraction of 0.07. 0.07. That's consistent. Now, would somebody like to help me with the mass percent? I will allow you to raise your hand. Let's see here. or just say me down in the bottom there if you would like to help me with mass percent. I need some help. Who's going to help? Wonderful, Alyssa. So, where would we start?
Well, do you want to find the mass percent of the water or the NaCl?
NaCl. No, sorry. Yeah, mass percent. NaCl. That's right.
Okay. So, well, we kind of already solved the grams of the NaCl in the former problem. So when you just do the 4.5 grams of NaCl over the 997 grams of solution.
All right. 204.5 grams of NaCl over which one?
The 997 grams of solution.
Okay. 997 grams of solution. So, 204.5 divided by 997. 0.205, is that right?
And you multiply it by 100 to get the percentage.
Okay, very good. %. All right, excellent. Those are so fun. We could do those all day, but we already did that last class, so we won't do it again. Okay, so now what we have are the tools and the understanding to go between molarity, molality, mass percent, mole fraction, and those are important for a couple of reasons. Some we will talk about in this chapter, and some we won't. But if we move forward now and introduce a law which governs the vapor pressure of a liquid, Now, let's put this, use a little bit of an experience on this to try to know or understand what this is talking about. So if I have a container here, and I have in this container something like alcohol, I'm going to call it IPA. That stands for isopropyl alcohol. Okay? This is the kind of alcohol that you'll have in your medicine cabinet. All right? Rubbing alcohol. All right? Isopropyl, prop. Anybody know what number prop represents in terms of, in our way of naming material? Prop, do you guys remember? We only did it a couple times in the past. There's meth, eth, prop. That's right. Prop is 3. And the iso, prop means 3 carbons, 1, 2, 3. And the iso means that on the second group here, the alcohol is coming off there. So you have isopropyl alcohol. And then there's hydrogens everywhere else decorating this compound. If I have a container of isopropyl alcohol, it will, if I just set it there on the table, it will relatively quickly, quicker than water, evaporate away. All of the molecules will find their way up through the air molecules and jump into the gas phase, from the liquid to the gas phase. Okay? If I have a container that is sitting on top of this container of isopropyl alcohol, what does that result in? The evaporated molecules that will begin to kind of fill this container results in something, a property that you get when you have a gas in a fixed container. What is that property, Landon?
Is it vapor?
It's a vapor is the material, and the resulting property that you have is a vapor pressure. In other words, there's a force applied by all these molecules which would try to push this box up off the ground. Right? So you have a vapor pressure. And if I had a similar container here, but I had water in my smaller vessel, right? And I allowed the water to evaporate. What do you think, Taewon? 2 containers. One has my isopropyl alcohol and one has my water in it, H2O. Both have a box, clear box on top that I can kind of see what's going on in there. Which one of these is going to have a higher vapor pressure, Taewon? Which one, the water or the isopropyl alcohol? Which one will have a higher vapor pressure? What do you think, Taewon? Which one will have a higher vapor pressure? The isopropyl alcohol or the water? Isopropyl alcohol. Very good. Isopropyl alcohol. And that's because the intermolecular forces that are pulling the molecules of isopropyl alcohol toward each other, holding them together, are much weaker compared to the intermolecular forces that are holding water molecules together. Okay? All right. So the vapor pressure depends on the intermolecular forces. Now, what happens when I mix isopropyl alcohol with water? All right. So I have a new container here that I'm going to draw. The new container contains a mixture of water and isopropyl alcohol. Okay. And the isopropyl alcohol in here would like to jump out and become a gas just like before. However, there's an interaction between the isopropyl alcohol and the water. We knew there was an interaction between the isopropyl alcohol and the water because they mixed together. They do mix together. You might not realize that, but when you buy rubbing alcohol, it's not 100% rubbing alcohol. It might be 90%, but generally people are buying something like 70 or 30% rubbing alcohol, right? And to get rid of the coronavirus and any other virus on your hands, you need to be making sure you use something that is at least 60% alcohol, which can be isopropyl, rubbing alcohol, or it could be ethanol, okay? Drinking alcohol. Now, yeah. Okay, so when you mix 2 compounds together, there's a shift in the resulting vapor pressure, right? And this is this law. Brielle, did you have a question or comment? This is the law that governs the resulting vapor pressure. It's dependent on the mole fraction of the solvent. All right? Now, how am I going to tell which is the solvent, the water or the isopropyl alcohol? Well, the solvent is always going to be the one that is in the higher concentration, So, if you take the solvent and then multiply it by the vapor pressure of that material, you take the, sorry, did I say the X of the solvent, the mole fraction, and then multiply it by the vapor pressure, that'll tell you the vapor pressure of the solution. What this also gets us to, gives us the ability to do is if I have a mixture of 2 compounds, if both of them have vapor pressures, then I can predict what the resulting vapor pressure of the solution will be by looking at the relative mole fractions of the 2 different compounds and their relative vapor pressures. All right, so that brings us to a problem like this, where we have 2 compounds, 2-methylheptane and 3-ethylheptane. All right, both of these compounds are volatile, and volatile is the word that means they will evaporate at room temperature. You put them in a container and then they'll gradually evaporate. All right, so 2 compounds, both of them volatile. what would be the pressure of a mixture of 78.0 grams of the 2-methyl and 15 grams of the 3-ethyl. Okay, so Sarah, what is the first thing I need to do if I want to begin to solve this problem?
I think we need to find how many moles of each thing we have.
That's right, because we ultimately need to get to the mole fraction, right? So I can identify how many moles of 2-methylheptane. I have 78 grams of it. So if I go, make this a little bit smaller now for a second. 78 grams of the 2-methyl. All right. I have a molar mass of 114.23. 114.23 grams for every mole of that material. This will tell me how many moles of the 2-methyl I have. All right. I can do that same thing with my 3-ethyl, 15 grams, 100.2 grams for every mole of the 3-ethyl. So this will tell me how many moles of the 3-ethyl I have. Okay, so if I want to identify the mole fraction of the individual components, then I'm going to do the moles of one, let's say the 2-methyl to start off with, over the moles of both combined, right? Could you guys solve for these? Let's see, Camille, can you tell us how much of this stuff we have? And Alyssa, can you tell us how much of that stuff we have? And then,
How many grams per mole for the ethyl?
oh, sorry, that's 100. Right down here.
I may need some help.
Okay, so what we're trying to do here is identify the moles of these two materials, the moles of the 2-methyl, and I know that I have 78 grams, and this is the molar mass, right? So, Alyssa, did you get it?
I got 0.15.
That's moles of my 3-ethyl here, right?
I got 0.68.
Okay, so if I go 0.68 over 0.68 plus the 0.15, could you tell me what that one is, Alyssa? And then Camille, you're going to help. Oh, no, Camille's doing this one. Sorry. Alyssa is going to help us with the other one here, which is 0.15 over the 0.68 plus the 0.15.
I got 0.81 or 0.82 rather.
Okay. Did you get this one, Alyssa?
Yeah, I got 0.18.
Which we're glad that these two add up to what? What should they have added up to, Landon?
They should have added up to 1.
Yeah, because those are the only two things in there, and these are mole fractions of the total, right? Okay, very good. So the pressure of the solution will be equal to the mole fraction of whatever A is times the vapor pressure of A plus the mole fraction of B times the vapor pressure of B. All right. So mole fraction of, let's say our first one, 0.82 plus the mole fraction of the second one, 0.18. What value do I put here, Landon?
Is it 233.954?
Uh-huh. All right, that's because that is our vapor pressure for our A, which we were using as our point, or 2-methyl, right? 0.82 is our 2-methyl. Okay, and then here, Aisha, what value goes here? All right. Very good. Whoops, equal sign. So, I'm just going to actually, instead of doing that on the calculator, I'm going to click right here. Very good. So, our resulting pressure, 230 torr, right? So our mole fraction of A times the vapor pressure of A plus mole fraction of B times the vapor pressure of B. Very good. All right, so Taiwan, if you want to look at this one for us, here's a second problem. Vapor pressure of 2-methylhexane, down here, is 37.986 torr at 15 degrees Celsius. What would be the pressure of a mixture of this stuff, of the 2-methylhexane and 15 grams of this stuff, naphthalene, which is nearly non-volatile at this temperature? All right, Taiwan. The last problem that we solved, ultimately, we said that the vapor pressure of the solution would be equal to the mole fraction of A times the vapor pressure of A, right, plus mole fraction of B times the vapor pressure of B. What if we use our 2-methylhexane as our A? What's the vapor pressure of A, K1? What's the vapor pressure of A? Very good. 37.986. So that we would multiply by our mole fraction. What about the vapor pressure of B, Taiwan? What would be the vapor pressure of B? If this B here is our naphthalene, what's the vapor pressure of naphthalene at this temperature? No, the vapor pressure of naphthalene here is, it says, 15 grams of naphthalene, which is nearly non-volatile at this temperature. Non-volatile means that it doesn't have any vapor pressure. So it's 0. So because it's going to be 0, we don't really care what the mole fraction is of this component. Right? All of this is going to drop out. So the resulting vapor pressure of the solution is just going to be equal to the vapor pressure of A times the vapor pressure of A times the mole fraction of A. So for this problem, we do the exact same thing as before, but we still need to find out what the mole fraction is. So we will have to find out how many moles of the 2-methyl and how many moles of the naphthalene. Add them together, right? Identify the mole fraction by taking our moles of the methylhexane over the moles total. But then after we get that, we just have to multiply that by our 37.986, and the resulting torr is the vapor pressure of the solution. Okay? Because naphthalene is not volatile at this temperature. Excellent. All right. So, this is another thing that you guys are probably aware of. Well, I think this is a good place